Hi, I'm Swarupa Sail, course instructor for Fluid Mechanics. In this presentation, we will go through applications of Bernoullis equation. Bernoullis equation is applied to all problems of incompressible fluid flow. It can be applied to measuring devices like venturimeter, nozzle meter, orifice meter, and pitot tube. Bernoullis theorem is used to study the unstable potential flow used in the theory of ocean surface waves and acoustics. It is also employed for the estimation of parameters like pressure and fluid speed. Bernoullis principle can be applied in an aeroplane. For example, this theory explains why aeroplane wings are curved upward and the ships have to run away from each other as they pass. Now we will study the practical applications of Bernoullis equation. It can be used for venturimeter, orifice meter, and pitot tube. Venturimeter is a device used to measure the speed and flow rate, that is, discharge of fluid through a pipe. Venturimeter works on Bernoullis equation. Its basic principle also depends on Bernoullis equation and continuity equation. Velocity increases and pressure decreases with the variation in diameter of the venturimeter. When cross-sectional area of the flow reduces, it creates pressure difference between the different areas of flow. This difference in pressure is measured with the help of manometer and helps in determining rate of fluid flow or other discharge from the pipeline. It has got three parts, that is, converging part where the diameter decreases. Then we have throat section. Then there is a diverging part where the cross-sectional area of the venturimeter increases. So the converging part is a starting section of venturimeter which is attached at the inlet of the pipe. The cross-sectional area of this cone starts to decrease and the converging angle is 20 degree and its length is 2.7 into T, that is diameter at the inlet section, minus small d, that is diameter of throat. The other end of converging part is attached with the throat. So throat is the middle portion of venturimeter and its cross-sectional area is very small. At this point, pressure decreases and velocity increases. One end is connected with the converging part and the other end of the throat is attached with the diverging part. Diameter of throat is 1/4 to 3/4 of the diameter of the inlet pipe, but mostly it is 1/2 of the diameter of the pipe. Diverging part is the last part of venturimeter and its cross-sectional area increases. Angle of diverging part is 5 to 15 degree. Its cross-sectional area continuously increases. One end is connected to throat and other end is connected to outlet pipe. The main reason behind the low diverging angle is to avoid the formation of eddies, because flow separation and eddies formation will result in large amount of loss in energy. So now we will study the working of venturimeter. Simple principle of venturimeter is when velocity increases, pressure decreases. Cross-sectional area of throat section is smaller than inlet section. Due to this, the velocity of flow at throat section is higher than velocity at inlet section. And this happens according to continuity equation. that is A1 V1 equal to A2 V2. The increase in velocity at the throat result in decrease in pressure at this section. Due to this, pressure difference is developed between inlet valve and throat of the venturometer. This difference in pressure is measured by manometer by placing this in between the inlet section and throat. Using this pressure difference value, we can find out the flow rate through the pipe. Now we will find out the expression for finding discharge, that is Q, through venturometer. So this is what is venturometer, which is having three sections, that is converging part, throat and diverging part. Converging part is connected to inlet of the pipe and diverging part is connected to outlet section. Let P1 be the pressure at inlet, P2 is the pressure at throat. Let the distance between datum line and center of section 1 be Z1, and similarly the distance between datum line and the section 2, that is throat, be Z2. The difference between the pressure head between section 1 and section 2 is H. So D1, P1, V1 and A1 are the diameter at inlet, pressure at inlet, velocity at inlet and area at the cross section 1. Similarly, D2, P2, V2 and A2 are the corresponding values at section 2. Now we will apply Bernoullis equation to section 1 and section 2. So we have P1 by W, that is W equal to rho into G. So P1 by W plus V1 square by 2G plus Z1 is equal to head at section 2, that is H2, and H2 can be written as P2 by W plus V2 square by 2G plus Z2. Since the pipe is along horizontal direction, Z1 is equal to Z2. This pipe is not inclined, so the value of Z1 is equal to Z2. And since Z1 is equal to Z2, we can rewrite this equation as P1 by rho G plus V1 square by 2G equal to P2 by rho G plus V2 square by 2G. And by rearranging the terms, we get P1 minus P2 divided by rho G equal to V2 square minus V1 square divided by 2G, and let this equation be named as equation 1. P1 minus P2 divided by rho G is the difference of pressure head at section 1 and 2, and this can be written as equal to H. So we will replace P1 minus P2 by rho G in equation 1 by H. So we get H equal to V2 square minus V1 square divided by 2G. Let this be equation number 2. Now we will apply continuity equation at section 1 and 2, that is Q1 equal to Q2. Q1 is area into velocity, so it is A1 V1 equal to A2 V2. So we get V1 as equal to A2 V2 divided by A1. So now substitute this value of V1 in equation 2. So by rearranging, we get V2 equal to A1 divided by square root of A1 square minus A2 square into root 2 GH. We know that Q is equal to A2 into V2. So we will substitute the value of V2 in terms of Q, because we need to find out the equation for Q. So Q is equal to A1 A2 divided by square root of A1 square minus A2 square into root 2 GH. So this Q is the theoretical discharge under ideal conditions, and actual discharge will be less than this theoretical discharge, and actual discharge can be found out using formula Q actual equal to CD into Q theoretical. So Q actual divided by Q theoretical will be equal to CD, and CD is nothing but the coefficient of venturimeter, and its value will be less than 1. Now we will find out how to get the value of H measured by differential manometer. Case 1, that is when liquid in pipe is lighter than liquid in manometer. So H will be equal to S, that is specific gravity, G or S minus 1 into Y. So S is equal to SM divided by SO. SM is specific gravity of liquid in manometer and SO is specific gravity of oil. And case 2, when liquid in pipe is heavier than liquid in manometer. So H will be equal to 1 minus S into Y. And S will be again SM divided by SO. Case 3 is inclined venturimeter with differential manometer, which contains a liquid heavier than the liquid flowing through the pipe. H will be equal to P1 by rho g plus Z1 minus P2 by rho g plus Z2, which will be equal to Y into SM divided by SO minus 1. And case 4 is when inclined venturimeter with differential manometer contains a liquid which is lighter than the liquid flowing through the pipe. So we get H equal to P1 by rho g plus Z1 minus P2 divided by rho g plus Z2, which will be equal to Y into 1 minus SM divided by SO. Now we will solve problem based on venturimeter. A horizontal venturimeter is provided in a pipe of 300 mm diameter conveying water. The throat diameter is 150 mm. If the pressure in the pipe is 160 kPa and the vacuum pressure at the throat is 350 mm of mercury, find the rate of flow in the pipe. Assume CD equal to 0.98. The given datas are D1 equal to 300 mm, D2 is 150 mm, P1 is 160 kPa. So we get P1 by W as 160 into 10 raised to 3, because here it is converted in terms of Newton per square meter, divided by W. W also is written in terms of Newton per cubic meter, so it is 9810. Since both P1 and W are in Newton, we get the value of P1 by W as 16.31 meter of water. And similarly, P2 by W is equal to, here it is mentioned that vacuum pressure at the throat is 350 mm of mercury. Since it is vacuum pressure, we use negative sign. So it is minus 0.35 into 13.6. It is mm of mercury. We need to convert it in terms of meter of water, because the liquid flowing through the pipe is water. Since we have to have same units for both P1 by W and P2 by W, we will convert mm of mercury into meter of water. So we get P2 by W as minus 4.76 meter of water, where 13.6 is the specific gravity of mercury. And H is equal to differential head, which will be equal to Z1 minus Z2 plus P1 by W minus P2 by W, which will be equal to 16.31, that is P1 by W, and P2 by W is 4.76. So we get H as equal to 21.07 meter of water. Here, since Z1 is equal to Z2, we have neglected the term Z1 minus Z2. Q actual is found out by knowing the value of CD, A1, A2 and the value of H. So CD is 0.98 into A1 is pi by 4 D1 square. So it is pi by 4 into 0.3 square into A2 is pi by 4 D2 square. D2 is 0.15. So rest of the term is square root of 2GH, that is 2 into 9.81 into H is 21.07 divided by square root of A1 square minus A2 square, with which we get Q actual as 0.1376 meter cube per second. Now we will solve one more problem. A 300 mm by 150 mm inclined venturimeter is installed in a 300 mm diameter pipe. The meter is at 30 degree to the horizontal, the throat section being 1 meter from the entrance. The flow of oil being up the meter. Pressure gauges at entrance and throat show readings as 150 kPa and 75 kPa respectively. If the coefficient of meter is 0.975, find the rate of flow of oil. Take specific gravity of oil as 0.8. Instead of the pressure gauges, the entrance and throat sections of the meter are connected to a differential manometer with mercury as the measuring fluid. We need to find the reading of the manometer. We will write the given data as D1 equal to 300 mm, which is equal to 0.3 meter. D2 equal to 150 mm, which is equal to 0.15 meter. Theta equal to 30 degree. P1 is 150 kPa and P2 is 75 kPa. CD equal to 0.975. G is equal to 0.8. We need to find out what is Q and what is Y. So to find Q actual, we have formula CD into A1 A2 divided by square root of A1 square minus A2 square into root 2GH. H is equal to differential head, which is equal to Z1 minus Z2 plus P1 by W minus P2 by W. In the problem, it is mentioned that flow is in upward direction. So we get Z1 minus Z2 equal to minus 1 sine theta. So it is minus 1 sine 30 degree equal to minus 0.5 meter. The inclination is given as 30 degree. So sine theta will be Z1 minus Z2 divided by 1. So we get Z1 minus Z2 as equal to minus 1 sine 30 and finally the value is minus 0.5 meter. Now we will find out what is P1 by W. P1 by W is equal to P1, that is 150 kPa. So 150 into 10 raised to 3 divided by W. W is not given. We need to find out the value of W knowing the value of G. The value of specific gravity is given as 0.8. So G is equal to specific weight of liquid divided by specific weight of water. So specific weight of liquid W is equal to G into specific weight of water, which is equal to 0.8 into 9810, which is equal to 7848 Newton per cubic meter. So once we substitute the value of W, we get P1 by W as 19.113 meter of oil. Similarly, P2 by W is equal to 75 into 10 raised to 3 divided by 7848, which is equal to 9.556 meter of oil. And the differential head H is equal to minus 0.5 plus P1 by W, that is 19.113, minus P2 by W, that is 9.556, which is equal to 9.057 meter. So Q actual is equal to CD, that is 0.975 into A1 into A2 into square root of 2GH divided by square root of a1 square minus a2 square. So finally we get 0.237 meter cube per second as Q actual. Now we have to find the value of Y. To find value of Y, we will use equation H equal to Y into Sm divided by So minus 1. So H is equal to Y into Sm, that is 13.6, divided by So, that is 0.8, minus 1. So we get Y equal to H, that is 9.057 divided by 16, which is equal to 0.555 meter. Now we'll find out what is orifice meter. It is also used to measure rate of flow of fluid flowing through the pipe. It works on the principle of Bernoullis equation and continuity equation. It is less costly compared to that of venturimeter. Venturimeter is expensive because of complexity involved in its design. Hence, in order to determine the rate of flow of fluid through these small pipelines, orifice meter is used compared to venturimeter. An orifice meter consists of one flat circular plate, and this circular plate will have one sharp circular edge hole bored in it. The circular sharp edge hole is termed as orifice. Discharge through orifice is found out using formula Q equal to CD into A0 A1 into root 2GH divided by square root of A1 square minus A0 square. Third one is pitot tube. Pitot tube is used to measure fluid flow velocity by converting the kinetic energy in a fluid flow to potential energy. So here we can see the flow of liquid through a pipe, to which there is a piezometer which is connected, which will measure only static pressure, and this is fixed at the wall of the pipe. Whereas the pitot tube is inserted into the pipe, and this will measure both static pressure and dynamic pressure. So the total pressure, that is stagnation pressure, is measured using pitot tube. The equation of velocity is derived by applying Bernoullis principle, and we can find out velocity using formula square root of 2gh, where g is acceleration due to gravity, and actual velocity VA can be found out using formula CV into square root of 2gh, where CV is coefficient velocity of pitot tube. Now we'll find out what are notches. A notch or a weir is a device which is used to measure discharge in an open channel. First one is rectangular notch. In the figure, there is a rectangular notch which is shown of length L and head of water in the notch is H. In this, consider a horizontal strip of water of length L and thickness dH, which is at a height of h from the surface of the water. Theoretical velocity of water flowing through the elemental strip will be square root of 2gh, and theoretical discharge will be area into velocity. So area of this elemental strip will be L into dH, and velocity is square root of 2gh. Now we have found out the theoretical discharge for only this elemental strip. if we want to find out the total theoretical discharge, we need to integrate from 0 to h. So, total theoretical discharge is equal to Q, which is equal to integration of this whole term. Here L and square root of root 2g is constant, so they are taken out, which are not varying. Here only h is varying. So we will integrate h from 0 to capital H. We get 2 by 3 into L square root of 2g into h raised to 3 by 2. So actual discharge will be equal to 2/3 of CD into L into root 2g into h raised to 3 by 2, where CD is coefficient of discharge. This is a triangular notch, and the actual discharge through this triangular notch can be found out using formula Q equal to 8 divided by 15 into CD into root 2g into tan theta by 2 into h raised to 5 by 2. So theta is this angle of triangular notch and h is the head of water in the notch. Now we will find out what are the advantages of triangular notch over rectangular notch. Triangular notch is always preferred over rectangular notch due to following reasons. First one is the expression of discharge for right angle V notch or wear is very simple. Ventilation of triangular notch is not required. Triangular notch will provide more precise results during measuring low discharge as compared to result obtained from rectangular notch. Only one reading of H is required for finding out discharge in case of triangular notch. Thank you.